All right, guys, today we take a look, a little deeper dive at sequences that are neither arithmetic nor are they geometric. So we talked a little bit about like your factorial pattern. We'll use some of that today. And then we'll also talk about where perfect squares come into play and fractions, different way to think about fractions with sequences. So your perfect square pattern, if I look at an equals n squared, so let's see, it'd be 1, 4, 9, 16, 25, that goes on and on. So if we think about addition, there is no common difference between these two, but this would be plus 3, gap here, plus 5, plus 7, plus 9. You can guess how that's going to keep going, and that's always going to be true, right? So 36 is plus 11, then plus 13, plus 15. The gap between numbers keeps increasing by 2, and that's a characteristic of your perfect squares sequence. So anytime you have that same pattern, even if the numbers aren't 1, 4, 9, 16, 25, so on and so forth, even if they aren't the perfect squares, if it follows the pattern of plus 3, plus 5, plus 7, plus 9, so on and so forth, it's going to be some variation of an equals n squared. It might be n squared plus 2. It might be n plus 5 quantity squared. It's going to have something to do with that pattern. We'll take a look at, I think, at least one in the notes here that deal with that. Fractions. Okay, a couple things about fractions. First thing is, if you ever have fractions that alternate, fractions in a sequence that alternate between positive, negative, positive, negative. Okay, so if fractions in a sequence alternate positive, negative, positive, negative. For all the negative ones, assign the negative to either numerator or denominator. And once you do that, because it can't be both of them, right? If the fraction is negative, it's either the numerator or the denominator is negative, not both, because then it would be a positive fraction. So look for patterns, and if you assign them all to the numerators, a lot of times the pattern will come out. Or sometimes if you assign them all to the denominators, the pattern will come out. We'll talk about that a little more with number 2 here, and then when we see an actual example. So second thing is look at numerator and denominator separately and try to identify a sequence for both of them individually. So maybe there's not one sequence that, or not one rule that defines your sequence, but maybe it's one rule for the numerator and one rule for the denominator, and I'll show you how we can put those together. Factorial, we talked about last week. Just real simple, know your factorial pattern. That's going to help you out a ton. You should just memorize these. You can figure them out a couple times, but eventually you should know that if I have an equals n factorial, 1 factorial, 2 factorial, 3 factorial, 4 factorial, 5 factorial, 6 factorial. Okay, I would know at least that far. Okay. What all the cool kids do. All right, they know at least 6 factorial and everything before it. Telling you. Okay. Now we need to find a general. Remember, that's explicit formula for each. I'm not doing 1 and 2. Those are simple arithmetic and then geometric. But let's look at number 3. So this is talking about our pattern with fractions. So if you look at the first term 2/3, then 3/4, then 4/5, then 5/6, this is not arithmetic. I can't add the same thing to get each new fraction. It's not geometric either. I can't multiply each fraction to get the next one. However, if I look at just the numerators, that's a pretty easy, capital N for numerator, that's a pretty basic explicit formula to write here, right? So if my formula, or if my sequence was just numerators, that's arithmetic, right? 2 plus 1 times n minus 1, right? Which gets me n plus 1. Denominator, it's the same thing except I start with 3, right? So 3 plus 1 times n minus 1, which gets me n plus 2. So when I put these together, I get an equals, and the numerator follows n plus 1, denominator follows n plus 2. And we can check this. Let me erase these circles real quick. So if I look for a1, I would do 1 plus 1, which is 2, 1 plus 2, which is 3, give me 2/3. If I look for a4, 4 plus 1 is 5, 4 plus 2 is 6, 5/6, right? So that works out. Let's look at 4. For first thing I'll do is everything's a fraction except for this first term. Let's turn it to a fraction. Next thing I notice it goes positive, negative, positive, negative, positive, negative. I'm going to take this negative sign and apply it to the numerators here. Okay? Which is the same thing. So let's just scribble those out. You can rewrite this if you want to. 1/1, -1/2. 1/3, -1/4. Now I'm going to do basically the same thing I did with 3, with problem number 3. My numerators, if my sequence was just the numerators, well, that's easy. That's from 1, -1, 1, -1. That's geometric. My first term is 1. My common ratio is -1, and then I raise it to the n minus 1 power. Denominator, same thing, 1, 2, 3, 4, 5, 6. An equals 1 plus 1 n minus 1, which equals just n by the time you distribute. Okay, so when I put these together, you get I get an. I like to save time by shortening words, so sometimes like I save one letter there. Instead of putting ER at the end, I put A at the end. Of course, I just gave some time back, but that's okay. All right, so I would have, I don't really need this 1, right? So on the top, it's a -1, the n minus 1, and on the bottom, it's just n. Okay. Number 5, let's look at this. So plus 3, plus 5, plus 7, plus 9. We said that's going to be a variation of perfect squares. So let's start with an equals n squared. Okay. Well, if I plug in 1, if I want my first term, the outputs from here are going to be 1 squared, 2 squared, 3 squared, 4 squared. Let's take a look at my actual sequence. The one I'm working with is 1, my actual one is 0. A2, the one I'm working with is 4, my actual one is 3. So how do I need to modify these? Looks like I need to decrease them all by 1, don't I? So that means that my sequence is not an equals n squared, it's an equals n squared minus 1. And now let's just double check. When I plug in 1 for my first term, 1 squared is 1, minus 1 is 0. When I want my second term, 2 squared is 4, minus 1 gets me 3. Okay, so it was a variation or a modification of the n squared sequence. Number 6, numerator. This is my factorial pattern, right? 1, 2, 6, 24, 120. So an equals my factorial pattern. Denominator, that looks geometric, right? First term 1, r value of 2. Putting together, I get an equals n factorial over 2 to the n minus 1. I think you can figure out 3. Geometric on top, arithmetic on the bottom. Okay, now we talk recursive. Remember, recursive, we always build on previous terms, right? I'm walking upstairs now. I can only walk up one floor at a time. On number 8, I have 1, 2, 3, 4, 5. I have 5 terms. The only one I can find with my recursive formula is the 6th one. That'll allow me to find the 7th one and the 8th one, okay? So again, I'm going to turn this into a fraction because everything's a fraction except for that first term. And let's take a look here. All right, so my numerator, 1, 1, 1, 1. If I'm thinking recursive, an equals an minus 1, what do I do to the previous term? Well, let's think multiplication. I'm just multiplying it by 1 because it's not changing. Denominator, 1, 2, 6, 24, 20. I recognize that as the factorial pattern. So unfortunately, it's a little trickier when we're dealing with recursive. Let's think multiplication again. How do I get from 1 to 2? Well, that's times 2. How do I get from 2 to 3? I'm sorry, from 2 to 6. That's times 3. 6 to 24 times 4. 24 to 120 is times 5. So I don't have a common ratio. I'm not always going to be multiplying the previous term by the same number, right? Up here, I was multiplying by the same number. I was multiplying by 1. Here, it's changing. So if ratio, that's what I'm multiplying by, if that ratio is changing, it must be a variable. Variables can change, right? So instead of multiplying by 2 or 10 or 8 or something at the same time, I'm going to multiply by a variable. Well, what's my variable? We're multiplying by n, right? For my second term, I'm multiplying by 2. For my third term, I multiply by 3. Fourth term, I multiply by 4. So what I'm going to do is for my denominator, it's an equals the previous term times n. Okay, so altogether, an equals your previous term times, the numerator was times 1, the denominator was times n. And you can plug in to check some of those. 9 and 10 I'm not going to go over. Typically in class I would get this far and then have you guys kind of work in groups to figure out 9, figure out 10. They're both a little tricky. All you're trying to do is, like for 9, using 2, how do you get to 3? Then from 3, how do you get to 8? What mathematical operations do you have to do? With 10, same thing. Using the previous terms, how do you get to the next terms? And this is actually your Fibonacci sequence on number 10, which you can look up if you're struggling a little bit with it. But that's about it for this. I will be live during your class period working through these notes. I recommend taking a look at this so that you're not seeing stuff for the first time. And I'll also have some office hours. Yeah, that's about it. I would love to have you guys come into the Zoom call if you can, because like I said in my post, it really is great to see you guys and be able to interact with you. Otherwise, it's just kind of me and a computer screen, and that's not fun for anybody. But I appreciate it, guys. Take care.